can't say more, it's not like before. So why am I hopelessly trying until I escape while I sleep, run to a place in my dreams, say hold on. Sometimes I just drive with street lights. Emotions on my mind, need to think twice.
Hey guys, so as you can probably see, my Swerve Drive has a lot of issues, one being that it can't actually drive straight well, and that is due to my design flaw. So in my design, my encoder steering motor, which actually rotates the module itself with the wheel, I'm using gears to connect them, so instead of something like pulleys or belts or chains, or just directly connecting the encoder motor shaft to the module to actually rotate it. And my gears that I designed have a lot of backlash, and that means that the teeth will have a lot of gap between them before they actually engage and rotate one another. So basically that means, say if I wanted to my module to rotate or my encoder motor to rotate like pi over 2 radians 90 degrees or pi over 4 radians 45 degrees. If I tell my encoder motor to move like 90 degrees, for example, then my module might only move like 87 or 85 degrees, which is really bad. So it's not going to be accurate all the time because of the backlash, and my module will be really loose until it actually engages with the encoder motor. So yeah, that's a big issue. And another issue is that since I'm using my encoder motors are relative encoder motors, instead of absolute encoders. So that means when I turn my thing on, before I turn it on, I have to manually, like, it's really weird. I have to manually align all the modules because they're relative encoders. They only care about when you turn it on. Oh, I'm at like 0 right now. Okay. If I move 90, then I just travel 90. But then when I get powered off and turn back on, well, 90 is my new 0. Oh, I moved 90 again. Oh no, I'm at 180 now. Something like that. But so, instead of absolute encoders, which actually can memorize their position even after a power down, the fact that I'm not even using to my advantage the fact that I'm using a 360 degree rotation module ability because I'm just using encoder motor to rotate it, and I don't think I'm ever gonna, cause like, okay, so say this is my module, so say it just moves here, like, and I want it to go like, okay, let me see, yeah. Maybe I wanted it to go back here, then like, the quickest way would just be like this, right? But sometimes, but another way would just to be all like that. So it's just, I'm not even optimizing it right now, which isn't good. So honestly, I'm thinking like, why don't I just use something like a servo that can, like I'll just use a really high torque servo that can actually like rotate the module to really accurate, precise degree instead of me having to use relative encoders with and my poorly designed gears modules that can't even align well. But anyways, the PID tuning of my encoder motors really helped a lot, because without the PID, it would be even less accurate. But yeah, that's pretty much it. So 2 major issues: I'm using relative encoders and my design. Okay, so I'm using relative encoders and my design is not accurate. Yeah. So I guess I'll talk about why I actually built this. So Swerve Drive is a very popular concept. I'm pretty sure it's been around for a very long time though, and like a lot of robotics competitions are now using Swerve Drive, like even BattleBots, and like NASA built like a Swerve Drive car a couple of years ago, and car companies are now building Swerve Drive mechanisms, which they call Crab Drive. But I'm pretty sure in terms of robotics, Crab Drive is where all your modules are literally physically interlinked with like a chain or whatnot. That way you can always guarantee your modules will be in sync with each other, pointing in the exact same direction. Well, that does limit your degree or freedom of movement, but in a Swerve Drive, all your modules are literally rotated independently, but that means one motor for each module, one steering motor for each module, and that adds more complexity, more motors, and it's more tedious, where you only need one motor for Crab Drive steering the modules. Yeah, people say Swerve Drive is more efficient than other land-based omnidirectional movement mechanisms like Mechanim wheels or Omni wheels or Crab Drive, I guess. Those are the only ones I know of so far, but I know of. But I'm not really sure why that's the case. But so people say because Mechanim wheels, the rollers are literally 45-degree angles. It's gonna wear out over time. It's like bad for the wheels too. Yeah, that's true, I guess. And also the force vectors of the 45-degree wheels just isn't efficient, I guess, which I guess is also true. But what I was thinking is that since standardly for a Mechanim drive you would probably have like 4 motors, whereas in a Swerve Drive, if you want 4-wheel Swerve Drive, you'd need 8 motors. That's double the motors, which means more power consumption from the battery, which in my opinion should mean less efficiency, but I'm not sure. But if your motors are, generally speaking, where all the motors draw the same amount of current or whatever, whereas well, you could maybe make like a 3-wheel drive, or 3-wheel Swerve Drive with only 6 motors in total, but that would still be more motors and more current draw. But still, maybe they cancel each other out at that point. Then efficiency from the Mechanim wheels, but less current draw versus the more amount of current draw from Swerve Drive, but more efficient wheels. I don't really know. And yeah, so Swerve Drive is a pretty cool concept I wanted to explore with this project. Me making an excuse for making this. But yeah, really, it's pretty. This is my Swerve module design. I'm pretty sure I showed you guys it in a previous video, but I'll show it again here, because why not? Yeah, so the drive motor essentially just sits on here, gets screwed in. This is the drive gear, connects to this driven gear, which will have the axle go through it and a flange coupling, so it's just screwed onto this steel axle. And a bearing goes on this main gear here, just inside of here. The bearing goes there, and then the steel axle goes through the bearing. Then the bearing comes out. Another bearing here, the steel axle comes out of here, then another bevel gear that drives this bevel gear, that therefore drives this gear, that therefore drives this gear, and then therefore drives this gear, and therefore drives the wheel. The steel axle goes through here. But yeah, so the thing is I had to manually drill the holes in the steel axle for the bevel gears, and that was pretty painful and tedious. But yeah, so then I forgot that for the driving gears, I did a gear ratio for higher torque. I forgot the gear ratio. I'm pretty sure this one was 21 teeth or something. I forgot how many teeth this was. But yeah, I think it was 14 to 21, so 2 to 3 ratio, but I'm not sure. I think this is 14 tooth, right? I'm not going to count it out, but anyways, 14 tooth, just a bit more of higher torque. And yeah, so then the encoder steering gear gets screwed on here, and this gear, the main gear, which gets screwed onto the module here. These brackets just hold the module in place, so if you lift up the robot, the module doesn't fall out. And so the steer gear to this main gear, this gear here, is a 1-to-1 ratio. So that makes the angles, I'm pretty sure there's 16 T's or something, I forgot. And there it's a 1-to-1 ratio, so it makes going to angles easier. So you just type in an angle and you don't have to do considering the gear ratio. And yeah, encoder motor gets screwed on here.